Collisions. A collision changes the particle's velocity. The kinetic energies of the individual particles will also change. Collisions fall into two categories. One is elastic collisions. In case of elastic collisions, the system's kinetic energy is conserved. And in case of inelastic collision, kinetic energy is not conserved. Some kinetic energy is lost during the collision. So it may be just convert into a frictional energy, or particular due to friction or due to produce in thermal energy. Okay. So the thing is that in case of elastic collision, kinetic energy is conserved. In case of inelastic collision, kinetic energy is not conserved. So momentum is conserved in both types of collisions. Now here figure shows some types of collisions. In first case, a ball rebounds from a wall, and in this case the velocity is changed. And second case, recoil of a rifle fires a bullet, causing the rifle to recoil. So in this case just there is a collision between the bullet and rifle, and in previous case the collision between the wall and the ball. Now the energy in the collision. So elastic collisions, kinetic energy is converted into potential energy and then back into kinetic energy. So kinetic energy is conserved in this case, elastic collisions. Okay. And in elastic collision, if the object does not return the kinetic energy to the system after the collision is inelastic. So kinetic energy after the collision is less than the kinetic energy before the collision. So there is a particular loss of energy, basically loss of kinetic energy in case of inelastic collision. Now here figure shows particularly collision or elastic collision. So here M1 and M2, two object with mass M1 and M2, and initial velocity is V1I and V2I, and the final velocity this is the after collision. The velocity, final velocity is V1F and V2F. Okay. So the principle, if you try to recognize the principle, external forces are 0, total momentum is conserved. So there is no external forces involved here. Okay. So sketch the problem. So to the right. So here just just sketch of the problem is given. So everything is along the x-axis. So this is a one-dimensional collision, which is called head-to-head collision. Okay. So in this case, we can just use the elastic collision condition. Kinetic energy is conserved here, and also momentum is conserved. Now, elastic collision example mainly. So in case of elastic collision, first identify the relationships. So elastic collision, in case of elastic collision, kinetic energy is conserved, and also momentum is conserved. So the equations are here. First one is conservation of momentum. M1 V1I plus M2 V2I is equal to M1 V1F plus M2 V2F. So here M1 and M2 are the mass of two objects, and V1I and V2I is the initial velocity of two objects before collision, and after collision V1F and V2F are the final velocity of objects. Okay. And if we apply the conservation of kinetic energy, the equation is half M1 V1I square plus half M2 V2I square. This is the initial kinetic energy, total initial kinetic energy of the system is equal to half M1 V1F square plus half M2 V2F square. So this is the final kinetic energy of the system. Okay. Now here figure shows another thing is that here two leaders pollute on an air track. So here initial mass M1 is 0.5 kg and M2 is 0.3 kg, and the initial velocity in opposite direction. So first one object A is rightward, velocity is rightward 2 meter per second, and velocity of object B is leftward, B is equal to minus 2 meter per second. So we consider rightward direction is positive, okay, or we consider the positive x-axis. So in case B, part B just describe the collision, and part C describe the after collision. So after collision, just they move opposite direction, and the velocity is final velocity object V is 2 meter per second, and you have to just find out the final velocity of object A. So just apply the momentum conservation law. Okay, so here m1 sorry ma va I plus m2 mv v vi is equal to ma vaf plus mv vf. Okay, so just if you apply the momentum conservation law, then we can easily calculate the final velocity of object A. Now in case of inelastic collision, so same things where we consider two gliders. Okay, so if two gliders just stick together and move just along just stick together and moves in the same velocity. Okay, so in this case the collision is called inelastic collision. So in inelastic collision, the total kinetic energy after the collision is less than before the collision. So a collision in which the bodies stick together is called a completely inelastic collision. So in this case, the figure shows a completely inelastic collision. In many collision in which the external force can be neglected, the total momentum is conserved. And here is also another figure shows another thing, example of the inelastic collision. Cars are intended to have inelastic collision, so the cars absorbs as much energy as possible. Okay, and here shows a sketch diagram. Okay, so object A represent the car 1 and object B represent the car 2. Okay, so they before collision they moves in opposite direction each other, and after collision they struck each other. Okay, then the velocity is along the same direction and velocity is same. Okay, now let's talk about the impulse. Okay, the change in momentum of an object due to a force that is applied during a period of time is called the impulse. So in case of impulse, the variable is called j. So j represent the impulse, and it's a vector quantity. So it's this impulse depend on the force, applied force, and the duration of the time period. And the thing is that the condition is, in case of impulse, force must be a very larger force, and time period is very shorter. So condition for impulse is force is very just greater, and time period is very short. So if we try to just give an example, the collision between bat and ball, normally cricket bat and cricket ball, is the example of the impulse. And the thing is that how can we find out the impulse? So impulse is equal to force into time. So J equal to Ft. Then the unit of the impulse is Newton second. Okay. Now let's if the particularly things we have to remember here, to hit a ball to the wall, both size of the force and the time of contact are important here. So bring both those together in concept of impulse. Another thing is that here object responds to amount of impulse. So large impulse, large response, so higher velocity, basically final velocity. So large mass, less velocity. Both mass and velocity play a role in how response to impulse. Now let's see the relation between impulse and momentum. So we know that according to the Newton's second law, F equal to ma, and acceleration is equal to Vf minus V naught divided by del t. Then if we put the value of the acceleration, force is equal to mvf minus V naught divided by del t, and mvf minus mv naught divided by del t, and finally f into del t is equal to mvf minus mv naught. So f into t, this represent the impulse, because multiplication of force and time gives the impulse. So here del t represent the time interval is very short, so that's why we have considered the del t, or you can also consider the time interval. It's represent the time interval. Okay, so the impulse momentum theorem state that impulse is equal to a change in momentum. So impulse j equal to del p, okay, which is del p is equal to mvf minus mvi, or ft equal to del mv. Okay. Now let's solve a problem related to the impulse and momentum. So a base ball with mass m equal to 0.14 kg with initial velocity of minus 40 meter per second, okay, basically 90 mile per hour, is hit. So here minus 40 meter per second, here velocity is negative, so the direction of the initial velocity is negative, we consider the negative. So it leaves the bat with a velocity of 60 meter per second after 0.001 second. So here time interval is very short. So I already said earlier, the condition is in case of impulse, time interval will be very short. Okay, what is the impulse and average net force applied to the ball by the bat? So we have to find out the average net force and also impulse. So now let's solve the problem. So according to the impulse momentum theorem, okay, F del t is equal to mvf minus mv naught. Okay, and here mass of the object is given 0.14 kg, and final velocity is 60 meter per second, and initial velocity is minus 40 meter per second. So if we put the values, 0.14 into 60 minus 0.14 into minus 40, which is equal to 40. Okay, so this 40 represent the impulse, because F cross del t is the impulse. So here impulse is 40 Newton seconds, and another here given unit is kg meter per second. So kg meter per second is also unit of the impulse. Now the force, so where average force mainly and force are same, because the force is variable force here, so that's why you consider the average force. So F equal to 14 divided by 0.001 seconds, so it's equal to 14,000 Newton. Okay, so here the force is very large and time period is very short. So these are the basic two conditions for impulse. Okay, so our answer is force is 14,000 Newton, and impulse is here 14 Newton meter. Okay, so these are the impulse 14 Newton second, and force is 14,000 Newton.